Word. Okay, so we want to find the derivative of this function k at x, which is f at x plus g at x. We're going to use first principles. So k prime at x would be the limit as h approaches 0 of k at x plus h minus k at x all over h. Well, k is f plus g. So this would be the limit as h approaches 0 of, instead of having k at x plus h, we're going to have f at x plus h plus g at x plus h. That's now k at x plus h minus k at x, which would be f at x plus g at x all over h. So we just wrote k in terms of this here. Okay, the square brackets only hold weight here. We can multiply the negative in. So we have the limit as h approaches 0 of f at x plus h plus g at x plus h minus f at x minus g at x all over h. Okay, this becomes the limit as h approaches 0 of f at x plus h minus f at x. I'm going to put the f's together and the g's together. Plus g at x plus h minus g at x all over h. And that can be broken into two fractions. So I'm going to break this into f at x plus h. Oops, I'm going to write that better. F at x plus h minus f at x all over h plus g at x plus h minus g at x all over h. Now we need to take the limit, and the limit of this whole thing will be the same as, so the limit of the sum is the same as the sum of limits. So we can do the limit of each one of these separately. So the limit as h approaches 0 plus the limit here as h approaches 0. And by definition, this is f prime at x, and this is g prime at x. So we can take this down and then say that k prime at x, that's what we started trying to find out here, is equal to f prime at x plus g prime at x. And then that's all summarized here below. Right? And then it asks for us to do a couple of examples. Okay, so we'll do those examples. Okay, where's my extended page here? That's odd. Well, we can fit them in here anyways. So f prime at x is equal to, okay, our rule. So we can go 2 times 3 is 6, x to the 1 or just x, minus 3 halves times 4. So that's going to be 6. 6x, and take 1 off the exponent. 3 halves minus 1, 1 half. 6x to the 1 half. And the other one, g prime at x, 2/3 x cubed. So we take 3 times 2/3 is 2. X, take 1 off the exponent. That's going to be squared. And the next one, just straight power rule, 4x cubed. Pretty straightforward stuff so far. Okay. Summarizing everything that we've done: power rule. We've done power rule, constant times the function, and sum and difference of functions. So, if we're given, if f of x equals x to the n, then f prime of x is equal to, you bring the exponent down in front, and then take 1 off the exponent. That's power rule. Okay, if we have f of x equals a constant times some function g at x, then the derivative is f prime at x is the constant times the derivative of the function. You're going to have to be reminded of this one later, because it's not the way we think of it with power rule. Okay? More about that later, but this is constant times a function. I guess constant times a function rule. Okay? And then the last one we had was, if we had h at x, for example, was equal to f at x plus g at x, then the derivative is, I'm going to say plus or minus here. Then the derivative, h prime at x, is f prime at x plus or minus g prime at x. So if we subtract here, we subtract here. If we add here, we add there. Right? So we want to look at, let's just do a couple more examples here. Oh, you need to see that? I'll leave that there for a minute. Okay. Well, we'll do 2 examples. So let's say we had g at x was equal to 4 times x cubed, the square root of x cubed, minus 9x squared. Okay? So if we have something like this, we need to deal with this thing. So square root as an exponent is exponent 1/2. Right? So this becomes 4x cubed to the 1/2. It's just the x cubed is to the 1/2 minus 9x squared, which is then 4x to the 3/2 minus 9x squared. And now we can find the derivative. So now I'm going to find it. So I made the exponent. I made this first term, and it's something we can actually differentiate. We haven't found the derivative yet. Now we're going to find the derivative. So now we change the notation. So 3/2 times 4 would be 6x. Take 1 off the exponent, 1/2, and then we're going to have negative 18. X to the 1, or just negative 18x. Now, this here, this negative 9x squared, this is constant times the function. But typically what we do is we just do 2 times the 9. Because that's going to happen. We saw that when we did constant times the function earlier. You're going to have to be reminded of the constant times the function rule when we get to other types of functions where we're not just multiplying a coefficient by an exponent. Okay, I'll have to remind you later in the course, because this is how people see power rule, and it's really constant times the function with power rule. Sort of like when we have trig functions, for example, we often don't have exponents, so the derivatives, or when we have logarithmic functions and so on, it's a different thing, and people forget what they're doing. Don't worry, when we get there, I'll go over it again. Okay, another place where people are going to fall down is in here. What some people will do is they'll take this thing and convert this this exponent like that. Great. What you really want to be able to do in the end is you need to be able to go from this to that in one step. There's just not time to mess around with it. If you see 4x cubed, the square root of 4x cubed, that's x to the 3 halves. Just boom, like that. Okay? The place where some people make mistakes is they'll go through this conversion, but they'll take this and write it like this right away. So they've written half of the thing they've written is derivative, and half of what they've written isn't derivative. You can't do that. It's all derivative or no derivative. Okay? So don't make that mistake. Right? You don't differentiate any of it until you differentiate all of it. Okay? Don't do little bits of it. There's something called partial derivatives you'll probably see in second year university. That's not what this really would be. It would be partially differentiated, but it's not correct. Okay, we'll look at another one. So let's say we have y is equal to 1 over x squared, that's a squared, minus 3 times the cube root of x. Okay, we've got to make this, now this isn't technically a polynomial function, but we can make it look like one. We can make this, we can work this with this power rule. What we need to do is write this as x to the negative 2. That shouldn't be new, because that's advanced functions. Okay? And the cube root, what's cube root as an exponent? 1/3. That's going to be minus 3x to the 1/3. Okay, we want to differentiate that. So, bring the negative 2 down in front. X, what's the exponent going to be? The exponent's going to be negative 3. Take 1 off the exponent. Negative 2 take away 1 is negative 3. And then we've got to go 1/3 times 3, or negative 3. That's going to be negative 1. X. And then we take 1 away from 1/3. Take 1 away from this exponent. Negative 2/3. Okay, that is a derivative. I'm going to use dy dx notation. Okay, often though, we're asked to write things with only positive exponents. So negative exponent means it's in the denominator. Right? So this is now negative 2 over x cubed and minus 1 over x to the 2/3. Okay, which I think I'll just leave it that way. X to the 2/3. It's kind of hard to read, but that's just x to the 2/3 there. Right? So if we have things that don't look like polynomial functions, we need to make them look like polynomial functions. Any exponent we can do that with. Okay. So now we're going to go on to, let's do, I don't know which one. Doesn't really matter which one of these we do first. Let's go with this one. Okay, so we want to graph this function. Okay, or we want to graph the derivative of this function. Okay, so it says here, click here to investigate the graph of the derivative. So I want everyone to push that here on their paper, see what happens. Nothing happens? No? Okay, let's try it here. Hopefully it works here. Apparently it does. Oh, there we go. Okay, so this is a different function. Oh, maybe there is. Thank you. No, that's not the original function. Doesn't matter. Let's look at this. We'll look at this one. Doesn't matter. Okay? Is it? Okay, well, it doesn't matter because we can do this anyways. Okay? So this particular function, okay? So if I move this point A along, no, maybe I have to move B. If I move B along, A moves with it, okay? And B is the tangent. So what we want to graph is, when we're graphing the derivative is the function that gives us the slope of the tangent for any x value. Here's the x value, right? There's the tangent. So, first thing I'm going to do is take this and measure that slope. So at that point, the slope is 21.75. Okay? Now I'm going to get just the x value here. So, for the derivative is a function that gives us the slope of the line tangent to the function at any point along the function. So for the derivative, this is the x, and that's the y. Does that make sense? So if I want to graph the function, the derivative, I could graph x, y. So that's what I'm going to do. So now when we move this along, there you can see that point. That point is tracing out the derivative. Okay, let's see what that looks like. I'm going to take that point and actually have it be traced. So we're going to trace that point and see what happens. I'll bring it back here. And as we move along the function, as the derivative moves along the function, you can see this tracing out. I just want to go slower in here and get more dots. Okay. Let's get some more in there. It just goes so quick right there. Okay, so you get the idea. Okay, so that red curve now is the derivative. Okay, first of all, what degree is the green curve? Polynomial function, what degree is it? Quartic. The green one's quartic. Degree 4? Okay, hey ladies. The green one is degree 4? What's the red one? Degree 3. Does that make sense? If I have an x to the 4 as my function, am I going to have an x cubed as this derivative? It's going to have different coefficients, but if I start with an x to the 4, I'm going to end up with an x cubed when I differentiate it. Okay, that's the first part. Okay, let's go back here. If we go back into this area in here, this is the slope of the, you can see the slope of the tangent. You can look at the number as it goes by. You can see it's extremely positive, like a slope of positive 30. That's crazy positive for slope. Okay? And as we move along, you'll notice it's getting smaller and smaller and smaller. When I get here to this maximum, and it's hard to get right on it, but what's the slope going to be at that point? 0. The slope is 0, and look at the derivative is 0, because the slope of the tangent is 0. So here the slope, everything got moved, but that's rather unfortunate. But here the slope of the tangent, it's pretty close. The slope of the tangent is getting smaller and smaller and smaller, and the derivative is coming down, 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 until we hit 0. Right? And then, what happens to the slope of the tangent? From here to here. It's negative. And you notice, the derivative comes down below. Okay, I'm just going to go back here and erase traces, and then we can do this again. So, in here, slope of the tangent is positive, but it's getting smaller and smaller and smaller, and it finally hits 0. Oh, right on. Perfect. Okay, and the slope of the tangent is 0, the derivative is 0. And in here, from here to here, the slope of the tangent is negative. And if you notice, all through this section, the derivative is below 0. the red curve is the derivative. It's below 0. It's negative. Make sense? Okay, and in here somewhere, it's negative, 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 negative to about here. Then it starts to get less negative till it comes back to 0. And then again, it's positive. And it gets more and more positive until some point in around here where it starts to get, right there, it starts to get less positive. And the derivative has a maximum there. That point is called the point of inflection. We'll learn more about it later. But in here, then it starts to get less positive. And when we get to the maximum here, if we can get there, the derivative should be at 0. Right there. Well, not quite right there, but in that area. Hard to get right on it. Pretty close. Okay, the derivative gets to 0, and then from there on, forever, the derivative is negative, and it just keeps getting more and more negative. The slope of the tangent just keeps getting more and more negative as we go. Does that make sense? So from a function, we can graph its derivative. Kind of. We don't know exactly where the maximum and minimums are going to be, and we certainly don't know right now where these points, because we don't know where the points of inflection are. We don't know exactly where they're going to be. We don't know exactly how high or low they're going to be. But we can do a decent sketch. So that's what the other page is about. Okay, so let's go back to this one. And it says, graph the derivative. Okay, well, let's start with where the derivative is going to be 0. The derivative is going to be 0, and I can barely draw it in, but down here, here, and here. That's where the slope of the tangent is 0. Everybody agree? So that's where the slope of the tangent is the derivative. So the derivative is going to be 0 here. At that point. Here at this point. And here at this point. Okay. We're starting with a quartic. Looks like we're getting 3 roots. We're going to get a cubic. Right? So, and then, okay, does everyone agree that on this interval, do this in blue, on this interval here, everybody agree the slope of the tangent there, everywhere on that part is traced in blue, slope of the tangent would be negative? Yes. Okay, so slope of the tangent is negative. The derivative shows the slope of the tangent. So all through, everywhere to the left of that point, the slope of the tangent is negative. The derivative is negative up to there. Okay? And then it becomes positive. From here to here, the slope of the tangent is positive. It starts off a little bit positive, gets more and more positive, till some point in around there, it starts to get less positive. Does that make sense? So it gets more and more positive, the slope of the tangent, hits some maximum steepness, positive, and it starts to get less steep or less positive until it gets back to 0. So right in point in line with that must be where the derivative gets a maximum. The derivative shows the slope of the tangent. The slope of the tangent in this interval, it hits a maximum there. So the derivative gets more and more positive to some point around here, then it starts to get less and less positive and comes back to 0. Right at that point. Slope of the tangent is 0. Right? All we're graphing is the slope of the tangent. Okay? Now on this interval, from here to here, the slope of the tangent is negative. It doesn't get very negative, but that's not really steep at all. But it reaches that maximum amount of negativeness right about there. Right? So the slope of the tangent is at 0, gets negative, negative, and then starts to get less negative as it heads back to 0. So the derivative must have a minimum in line with that point. It gets more negative and then reaches some maximum negativeness and heads back towards 0. So that root again is right in line with where the function has a minimum. The slope of the tangent is 0 there. And then the last part of this, from here on, the slope of the tangent is positive and it just keeps getting more and more positive. So the derivative must look something like that. This is f prime of x.
Was the first part all negative? Like at the start of the function?
This, yeah, from here to here, the slope of the tangent is completely negative. So this is all negative. It's below 0, right? What you have to know, like when we're graphing the derivative, we're graphing its y values. Its x values are the same as the x values of the function. Its y values are slopes of the tangent. That makes sense. Slope of the tangent is negative from here to here. The derivative is negative from here to here. Right? Slope of the tangent is positive from here to here. The derivative is positive from here to here. Slope of the tangent is negative from this point to this point. The derivative is negative from that point to that point. And then the slope of the tangent is positive for the rest of this. So the derivative is positive for the rest of this. And increasing. That makes sense? Okay. So if we go to, what's going on that page? Okay, here's one. This is the next one you guys have?
Yeah.
Okay. So if we want to graph this one, the derivative of this, right? Start where the maximums are. Where the maximums are, here and minimum, here and here, that's where the derivative is 0. The slope of the tangent is 0. So the slope of the tangent is 0 right here, and the slope of the tangent is 0 right here. So the derivative is 0 in those 2 points. Okay, we're starting with something that looks like a cubic. We should end up with something that looks like a quadratic, or a parabola. The cubic's increasing, so its leading coefficient is positive. So the leading coefficient on the parabola should be positive, so the parabola should open up. Okay? Now, don't worry about what the y values of the function are. What are the slopes of the tangents? Slope of the tangent here would be positive. I don't care what the y values are, the slope of the tangent is positive. Slope of the tangent is less positive here. Slope of the tangent is very positive, gets less positive until it hits 0. We're graphing the slope of the tangent. Slope of the tangent is positive, it keeps getting less positive until it hits 0. From here to here, the slope of the tangent is negative. That makes sense. The function's going downhill. If it was a series of little short lines, they'd all have a negative slope. Not very negative here, maximum negative right in around here somewhere, and then not very negative again. Where it hits its maximum negative, so the derivative is just the slope of the tangent, so coming negative, it hits its maximum level of negativeness, and then heads back to 0. Slope of the tangent is 0 there. And then from that point on, from here on, slope of the tangents are positive and getting more positive. Everybody agree? So the derivative is positive and getting more positive. And we get something that looks like that. And it's 1 degree less, as it should be. Power rule indicates that if you have a polynomial function, your derivative is going to be 1 degree less. So if we go from a cubic function, then its derivative should be a quadratic function. This appears to be that, more or less. It's not a great parabola, but, you know, best we can do right now. We do that one?
Oh, yeah.
Okay. Is this the next one you had? Okay. What does that look like? That looks like sine. No, that looks like sine. Okay, we can't say for sure that it's sine. What looks like sine? Probably a sine. some version of sine anyways. You're going to find something really interesting here. Okay, based on what you know about just about anything, there's a maximum there, so the slope of the tangent is 0 there. Everybody agree? There's a minimum here, so the slope of the tangent is 0 there. So our derivative is going to have a root there and a root here. There's a minimum here, so the slope of the tangent is 0 there. So the derivative is 0. The derivative will have a root there. The slope of the tangent at this point is 0. So the derivative is 0 at that point. The derivative will have a root at that point. Okay, now, the other thing we know is, because if we assume this is a sine function, then we know exactly where it changes from concave down to concave up, right? Which the concavity is going to change at these points, right? What you know about sine, it is concave down, then it's concave up, right? And that changes right here at its roots. Okay, well, let's start to graph the derivative, okay? So, slope of the tangents here, always positive, getting less positive until we get to 0. Does that make sense? So, slope of the tangent, I'm just going to draw a little bit. I don't know exactly what's going to happen closer to the y-axis. So just draw a little bit here. Slope of the tangent positive, heading to 0. Oh, heading to 0. Maybe I should redraw that. All I know here is slope of the tangents are positive, headed to 0. After this point, in this interval, slope of the tangent's negative. Reaches its most negative point there. It's still negative here, but it's headed back to 0. Right? So, in here, slope of the tangent is negative, reaches its maximum negativeness about here, and then heads back to 0, where the slope of the tangent is 0. Make sense? Okay, let's go back the other way. Let's take this back the other way. All we really know is that from this point on, all we can say right now, from this point on, the slope of the tangent is positive, so it must take off like that. Okay. If we go back the other way, on this whole interval in here, so I'm going backwards now, but here, on this whole interval, the slope of the tangent is positive, right? It reaches its maximum positiveness right at that point, until it gets back to 0. So the slope of the tangent is positive, it reaches its maximum positiveness here, and then it heads back to 0 here. On this next interval, going backwards again, this interval, the slope of the tangent is 0, or is negative. It reaches its maximum negativeness right there. And then heads back to 0. So it reaches its maximum negativeness. Now the slope of the tangent is getting less negative and headed back to 0 right here. Geez, what's it look like going on here? If I just continue this pattern, this end must finish off like this, and this end must finish off like that. The red function is the derivative. And it appears that if the original function f at x is sine x, it appears that f prime at x is, it looks like cos x. Maybe it is. We can't say for sure yet because we don't know exactly where those points are. Maybe it's 2 times cos x. Maybe it's 1/2 cos x. But we can say generally the shape. We just don't know how high the maximums and mins are. But it looks like cos x if the original sine is. Okay? Okay, you only get good at this by practicing it. We'll do, I think this is the last example I have, and then some labels. Okay, so, okay, here again, we have a cubic. So we should get a quadratic parabola. So, let's go to the maximums here and minimums. The slope of the tangent is 0 at these 2 points. So the derivative should be 0 at those 2 points. Okay? In between those 2 points, in here, the slope of the tangent is always negative, but it reaches its most negative point somewhere in here. So it's negative, 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 starts to get less negative, back to 0. So somewhere in here, this thing reaches its maximum negativeness. So slope of the tangent is negative, 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 hits a maximum negativeness, and goes back to 0. Okay? And on either side of this, if we go to the right of this root, the slope of the tangent is always positive and just getting increasingly positive. So the derivative is always positive and getting increasingly positive. And on this side, to the left of this root, the slope of the tangent is also always positive. If you look at this left to right, it's also always positive, but it's getting less and less positive and eventually gets to 0. The slope of the tangent here on this side looks something like this. Or is that in blue? Looks something like this. And we get something that looks like a parabola. And that's f prime at x. That make sense? Okay. I'm going to leave those blank ones. There's some homework questions you're going to have to draw derivatives and stuff. So I'll just leave you those ones to work on. Maybe we'll do some examples later. Tomorrow. Now I want to go on to the application handout. Okay? So, applications of derivatives. Okay. So, one application is this first question. Determine the equation of line tangent to some function at a point. So, this is some cubic function. I don't care so much what it looks like, except to know that it's a cubic function, right? At some point, x is going to equal 4 on that function. Does this make sense? Okay, so I'm just going to go to a blank page to work on this. But essentially, here's what's happening with number 1. We know we have a cubic function, and it's an increasing cubic function. Does that make sense? Okay, so I'm just going to draw it like this. Because theoretically, it doesn't matter what the function looks like or what the point is. It works the same all the time. So here's the function, and we want to find the equation of the line tangent to it. So let's say we want to find the equation of the line tangent at this point. That line would look something like this. Does that make sense? Okay? If we say this is the point, I'm just going to say this is the point A, C. I don't want to use B. Just say it's the point AC. That makes sense? Okay. Then the slope of that line is going to be, if the function is f at x, then the slope is going to be f prime at A, at that x value. Does that make sense? The derivative is the function that gives us the slope of the tangent. Does that make sense?
Yeah.
Okay? And then, if I want to figure out the equation of a line, y equals mx plus b, we've got the slope, we've also got a point. So we can put the x value there, the y value there, and solve it for b, and we have the equation of a line. Once you get the slope and the point, it's a grade 9 question. Right? Okay. So first thing we need to do is figure out the derivative. Right? So, come on, go away. I don't want music.
Okay, maybe if you something over.
Go away. Oh, there's the X now, wouldn't you? Okay, that's all on video, by the way. Okay, so the equation of the line is going to look like this. Y equals mx plus b. This over here is all just kind of rough work, right? So the equation of the line is y equals mx plus b. M is going to be, okay, y prime, since the function is y, f is going to be y prime evaluated at x equals the point of tangency 4. Okay. Okay guys, that make sense? Don't just like, listen, I was talking to a first year university student, and he's telling me that if you think you're going to go to university and take math and just like know how to do this stuff, just know the steps, forget it. You'll fail. You've got to understand, so you need to pay attention. Like I can show you the steps and you can reproduce them. But if you don't understand it, you're going to apply it to other things. And you're going to be lost. Okay, so we want the derivative first. The function y is x cubed minus 3x squared plus 12. So y prime is 3x squared minus 6x. What's the derivative of 12? I don't know, we talked about the derivative of constant.
It's nothing.
It's like 12x to the 0.
Oh,
No, it's like 12, it's like,
oh, and then,
so 12x to the 0, multiplied to 0 times 12, we got 0x to the negative 1. Well, that's 0. Right? That's 0. So the derivative of 12 is 0. Okay? Now, m is that thing evaluated at 4. I already said that, right here. So m is going to be 3 times 4 squared minus 6 times 4. 4 squared is 16, times 3 is 48. 6 times 4 is 24. 48 minus 24? 24. Okay, so here's what we know. So far we've got y equals 24x plus b. We need a point to plug in there. We got the x. We want to know, we got an x value 4. Right? Can we get a y value that goes with that? Okay? So the y value, if we go back to this drawing over here, that point is the only point on the curve and on the derivative, or on the tangent, right? So we've already got the x value. To get the y value, take the x value, plug it into the function, and you'll get the y value. And we have that point of tangency, right? So we need to find the point of tangency, what we're doing. So, the point of tangency okay, that's what we're trying to find. When x equals 4, y equals, plug 4 into the original function. 4 cubed minus 3 times 4 squared plus 12. 4 cubed, anybody know what that is? 64, you're right. Okay, 64. 3 times 4 squared, we just did. Goodbye. We don't want that. Okay. 3 times 4 squared is negative 48 plus 12. 28? Is that right? I'm pretty sure it's 28. It's 28. So we can take those values now and sub them in here for x and y and solve for b, and we'll have the equation on the line. That makes sense? Now, your normal solution is going to have these lines all over it. Right? So now we have then, so when we put a 28 in for y into the equation on the line here, we've got 24 times the x value is 4 plus b. Okay, 4 times 24, 96 plus b. Subtract 96 from both sides. Is it negative 68? B equals negative 68. Therefore, the equation of the tangent is y equals 24x plus b, or minus 68. And if you look at our drawing there, you know, there's no x or y axis there, but we got a really steep line with a really big negative y-intercept. Makes sense. Right? Okay. Everybody okay with that? So those questions are just like an exercise in doing calculus. Right? Okay. We'll go on to the other application question. So the displacement of a particle. So this isn't a lab. Somebody's doing something to make stuff move. I don't know what. Okay. For our purposes, the particle is either moves up, down, or left, right. We'll go left, right. So if the particle is moving to the left, its direction is negative. If it's moving to the right, its direction will be positive. Right? So it might be moving back and forth. Probably is. Okay. We want to determine the position of the particle at t equals 1 and t equals 4. Well, that function gives the position of it relative to where it started. Does that make sense? It's displacement relative to where it started. It started at position, when t would equal 0, then x at 0 would be 0. Agreed? So the function is as it moved. Right? So the particle hasn't moved at t equals 0. So first I'm just going to write down the function. S at t equals negative 0.5 t cubed plus 2t squared. So again, S at 0 would equal 0, meaning that when time hasn't gone by, the thing hasn't moved. Makes sense. We're measuring its displacement after t equals 0. It doesn't tell us, but I don't know, well, we certainly don't know what unit the displacement is measured in. T is probably in seconds. Okay, anyways, we want to determine the position of the particle at t equals 1. This is no calculus here, right? We just plug those values into the function. So, we want S at 1. That would be negative 0.5 times 1 cubed plus 2 times 1 squared. Well, 1 cubed is 1. So we get negative 0.5. 1 squared is 2. This is going to be 2. So at 1 second, the displacement is 1.5. Right? And we want to know the displacement at t equals 4. So that would be S at 4. That would be negative 0.5 times 4 cubed plus 2 times 4 squared. 4 cubed is 64. We're negative a half of that, negative 32. 4 squared is 16. Plus 2? 32. 0. What's this mean?
That's what it makes up. Not
Oh, it's not the derivative.
that's what it is from the roots.
And so what's happened to the particle? Yeah, Josh. It's gone back to where it started. Now we don't know, like, the particle started out here, going to the right. It's gone back to the left here, and gone back to 0. But we don't know how many times it may have changed direction in between. We just know originally it's going to the right. and then s equals 4, and then it's back to where it started. Might have gone by that starting point 20 times. We don't know. Right? Okay. So, I'm just going to say here, when t equals 1, s equals 1.5, and when t equals 4, s equals 0. Okay, next question says, determine the velocity of the particle at t equals 3 and t equals 5. Okay, the velocity. The velocity is instantaneous rate of change in position. Your velocity is your rate of change in position. We want to determine the velocity of the particle at t equals 3 and t equals 5. That means instantaneous velocity. This is velocity, it means at that instant. Okay? So, for B, velocity is equal to, well, I'm going to change it. V at t would be the velocity. That's the instantaneous rate of change in displacement. As your position changes, okay, the rate at which your position changes is your velocity. The instantaneous velocity is the instantaneous rate at which your position changes. That's the instantaneous rate at which the displacement changes. The instantaneous rate of change is the derivative. Right? So your instantaneous rate of change in position is velocity. That makes sense. The next question deals with acceleration. Acceleration is the rate of change in velocity. You want to know your acceleration at a point? That's your instantaneous rate of change in velocity at that point. That makes sense? See the applications, they just keep coming. There's going to be more and more and more. Okay? But, so, velocity is s prime at t. Well, s prime at t is negative 0.5 t cubed plus 2t squared. S prime at t then is going to be, take the 3, multiply by negative 0.5, you're going to get negative 1.5t, 1 off the exponent squared, plus, we're going to have the exponent 2 times the coefficient 2 is 4, t, take 1 off the exponent 1, or we don't have to bother writing that. It's even best not to write it so we don't confuse it with prime. There's the derivative. So v, we want the velocity at 3. V at 3 equals s prime at 3 equals negative 1.5 times 3 squared plus 4 times 3. Well, that part's 12. This is negative 1.5 times 9. Negative 13.5, right? We need a plus in here. So that's negative 13.5 plus 12, negative 1.5. That's the velocity. The velocity is negative. What's it tell us? It's going back. The velocity, remember from the vectors part of the course, velocity includes direction and magnitude. The magnitude is 1.5, the direction is negative. So if we're thinking right and left, this is going to the left. Right? We don't have a unit, so we'll just leave that. Okay. For whatever reason, it's not letting me extend the page. So I'll have to do the second part of this on the next page. So now, V at this point with 5, right, is going to be equal to S prime at 5. So that's negative 1.5 and then 5 squared times 5 squared plus 4 times 5, right? Okay, that's negative 1.5 times 25 plus 20. This would be a half, this is 1.5 of these, so that's 37.5. Right, negative 37.5. Negative 37.5 plus 20, negative 17.5. So the object moves to the left at 5 seconds, or 5, whatever, as well. That makes sense? And pretty fast compared to what it was doing at what was the other time? 3. Right? Okay. Determine over what period of time the particle is moving to the left. And over what period of time the particle is moving to the right. Okay. What do you think? Which direction is it moving here? Left. How would we know if it was moving to the right? Would have a negative. So, when V at t is greater than 0, which way is the particle moving? To the right. When the velocity is positive, it's moving to the right. Okay? Velocity is magnitude and direction. Positive direction is going to be the right, negative direction to the left. Right? So when V at t is greater than 0, the particle is moving to the right. When V at t is less than 0, which way is the particle moving? To the left. So when V at t is less than 0, the particle is moving to the left. What about when V at t equals 0? It's not moving, or it could be changing direction. Right? So if you're moving this way, and you stop and move this way, and you're going that way, and you stop, move back, right there, just for an instant, your velocity is 0. Not moving either direction. Right? Just for an instant. Okay, so when the velocity equals 0, the particle is not moving or changing direction. That's an R. Changing direction. Okay. So if we want to know when it's moving to the left and when it's moving to the right, we need to know when the derivative is positive and when the derivative is negative. Okay, I'm going to have to go to the next page. So this is C continued. We need to know when, it was S prime at t. When V at t, or S prime at t, is positive. That's how we'll know when it's moving to the right. Okay, the derivative is S prime at t is equal to negative 1.5 t squared plus 4t. We want to know when negative 1.5 t squared plus 4t is greater than 0. Well, why don't we, the 14 needs to be bigger than the other one. We'll solve this as though it equals 0. Right? So we can factor out a t here. Right? Okay, so we'll factor out a t. T, and we'll have negative 1.5t plus 4 greater than 0. Okay. T is always positive. Time can only move forward. So t is either 0 or positive. Everybody agree? So that's always going to be either 0 or positive. So this thing's going to be we're going to determine whether this is positive or negative by finding out when that's positive. Does that make sense? So we want to know when negative 1.5 t plus 4 is greater than 0. Or when negative 1.5 t is greater than negative 4. Okay. I got to show you something here. Okay. Does everyone agree that 7 is greater than 3? If I divide both sides by negative 1 or multiply both sides by negative 1, we get this. Is that true? No. So when you multiply or divide an inequality by a negative, you need to change the direction of the sign. Of the inequality sign. This actually needs to go this way. Okay, so we're going to divide by negative 1.5. We need to change the direction of the inequality sign. So we're going to have t is less than negative 4 divided by 1.5. Okay. What do we get? Not quite 3. 2.67? Okay. 2.67? Okay. Similarly, if we want to do the negative for s prime at t is negative, we're going to do this. We're going to take the same thing. We're going to have t times negative 1.5 t plus 4 less than 0. So we're just going to s at t less than 0. S prime at t less than 0. Well, t is always 0 or 1. So the sign of this is going to be determined by this again. We have negative 1.5 t plus 4 is less than 0. Negative 1.5 t is less than negative 4. Divide by a negative, we're going to change the inequality sign, the direction of it. T is greater than negative 4 divided by negative 1.5. T is greater than 2.67. So apparently, this thing is always moving to the left. If t is less than 2.67, sorry, no, always moving to the right if t is less than 2.67. This is going to the right, and this part's going to the left. Does that make sense? And when does time start? Time starts at 0. Okay, so from t equals 0 to t equals 2.67, the particle is moving to the right. And from t equals 2.67, I'm just going to say onward, I guess it would be forever, okay? The particle is moving to the left. So somebody might be in a lab studying motion, studying, maybe this has something to do with electromagnetic fields, maybe this has something to do with like hitting something with radiation, whatever, and they just want to know like what goes on. Right? Okay, so this would be a much, this problem would be a very small part of a much bigger problem. Okay. The last part, it says determine the acceleration. Acceleration is instantaneous rate of change in velocity. Okay, so for D, do you guys still need to see that? Okay, so for D, Okay, velocity at t is equal to s prime. So velocity is instantaneous rate of change in position or displacement. Acceleration is the instantaneous rate of change in velocity. It is the derivative of the derivative, or the second derivative. Okay, from previous questions, we know that the velocity is negative 1.5 t squared plus 4t. That's right, isn't it? So then, the acceleration, which is equal to v prime at t, is the derivative of this thing, negative 3t plus 4. It's a straight line. Right? So, okay, so we want to know the acceleration. We want, what do we ask for? A at 1 and A at 4, right? So A at 1 would be equal to negative 3 times 1 plus 4, negative 3 plus 4, it's 1 meter per second or whatever. We're never given units, so whatever the units are. That make sense? And A at 4 is negative 3 times 4 plus 4 is negative 12 plus 4 is negative 8. What does that mean? Acceleration is negative 8. No need?
Or it's decelerating.
It's decelerating, slowing down. Okay? Okay. So, there's on the homework questions, there's questions related to this, and it asks for average velocity. So, let me tell you this. If you're looking for the average rate of change, you've got delta y over delta x, or y2 minus y1 over x2 minus x1. You're looking for the slope of a line where you got 2 points. Average, right? You might have a curve like this, and you want an average rate of change from those 2 points. Between those 2 points, you find the slope of that line at secant. If you want instantaneous rate of change, and we start with y, we're going to use dy dx. So the notation's similar. Delta y over delta x, x2, or y2 minus y1 over x2 minus x1, average. Dy dx, instantaneous. Okay, so you've got the sheet with the homework questions on, right? The front page is just draw the derivative. Is it? Keep in mind, it would be fair for me to give you a quote. We won't do it yet, but I can give you the graph of the derivative and say draw the function. Okay, we'll look at that later. And then the back is all questions related to what we did on this last syllable. Okay, so the questions will require you to think. So think. Okay? And just sit. So we can stop the video.